Let's return to this idea of differentiating exponentials. So y equals e to the power of any function of x. So we saw e to the power of x yesterday, the basic one, and we saw that, all right, the slope of the tangent at x equals 0 was 1, and it made life nice and easy. But of course, trying to work out the slope of every different curve at x equals 0 is time consuming. Let's see if there's an easier way. So e to the power of function x, I'm going to just let u equal some function of x, whatever that power happens to be. So now I've changed it to be y equals e to the power of u. And I'm going to differentiate this with respect to x. But of course now the pronumeral is u, it's not x. So I'll use our chain rule, implicit differentiation, rates of change, whatever you want to call it. But I'll differentiate e to the power of u with respect to u, but I'll have to multiply it by du dx to balance it out. Differentiate e to the u with respect to u, we get e to the u times the derivative. Well, hang on, f dash x. Well, I can now rewrite it. It's simply going to be differentiate whatever the power is. That'll go in front, and we'll have e, and the power doesn't change. So unlike polynomials, we don't take one off the power. Okay, so there's our rule. That'll save us some time. If we're differentiating e to the power of function x, basically we just differentiate the power. That goes out the front, and that's e to the function x. Well, that's if it's base e. What if it's any other base? So I've got a to the power of function x. I could change the base. Now, I'm not going to do that now, but essentially we could rewrite that as a log, then use our change of base rule for log, so we could get it into e to the power of something, then convert it back, and then we could differentiate it via our new rule. But what ends up happening is this. Essentially, it's exactly the same. The only difference is we end up multiplying by the natural log of a, the base. And that comes from the change of base rule. Okay, let's do some examples. If we ever get this question, we say thank you very much. It's the world's easiest derivative. Y equals e to the x. The derivative is e to the x. Thanks for coming. All right. But now we can do ones like this. E to the power of 5x, we just differentiate the power. Differentiate 5x, you get 5. So it's 5e to the 5x. E to the 4x plus 3, just differentiate the power. We'll get 4. 4e to the 4x plus 3. That doesn't have to be a linear function. E to the power of x squared plus 3x plus 2. Differentiate the power, we get 2x plus 3. E to the power of x squared plus 3x plus 2. So now let's answer this sort of question. If I want to find the actual tangent, the equation of the tangent to y equals e to the power of 2x plus 1 at the point 1, and I've written the exact value down there for the y value, e squared plus 1. Want to find the equation alone, we need two things. We need a point, we need a slope. We've got a point, let's find the slope. And that's where we're using a calculus. So y equals e to the power of 2x plus 1, differentiate that, we get 2e to the 2x. Now that's not the slope of the tangent. That of course is the formula that allows us to find the slope of the tangent. Sub in the x value, which was 1, and we get 2e squared. So all right, point slope formula. Y minus, well the y value was e squared plus 1, equals 2e squared times x minus 1. Expand out, I've put it in general form. It looks strange because of those e squareds, but remember, it's just a number. It's an irrational number, e squared, so it's the same as any other number. So we get 2e squared x minus y minus e squared plus 1 equals 0 would be the equation of the tangent. Here's one where the base is not e, but what we said was we'll do it exactly the same way. The only difference is we also have to multiply by the log of 4. You notice I put the log of 4 in parentheses there. That's just to avoid any confusion. I mean, imagine that I didn't put the parentheses around that. Then you might look at it and think you're saying log of 44 to the power of x squared. Or if I'd put the log 4 first to try and solve that problem, then maybe I'm saying the log of 42x. And so to make it very clear what we're multiplying, I'll whack some parentheses around that. Let's look at this natural logarithm in a bit more detail. Okay, so the inverse to the exponential base e is the natural logarithm. So if y equals e to the power of x, then x equals the log base e of y. Of course, there are alternative ways you could write this. You could write ln y as one way of doing it, or you could write just log y. So if we don't see it, we assume it is a natural logarithm. Yeah, it's probably safer to write ln, avoids any confusion at all. But what I'm saying is if you just see log y, you assume they're talking natural log. So if I had to simplify the natural log of 1 on e, well, 1 on e can be rewritten as e to the power of minus 1. Log laws, I can bring that to the front, I get minus log e, but log e is 1, so we get negative 1. E to the power of 2 log 3, I could cancel, but before I do, I need to bring that 2 into the log. Now it's e to the power of log, we got inverses, so they will cancel, leaving me with 3 squared, which is 9. C, D, and E. Oh.